All right, so here we're going to take a look at the comparison test. Now, before we jump into the comparison test, some something that'll be helpful here in establishing inequalities here is when we have a fraction here, right? If we add something to the denominator, right, we're making the fraction actually smaller, right? So if we think of this and we're adding 1 to this, thing where you get 1/3 is less than 1/2, right? So when we add positive numbers in the denominator, the fraction becomes smaller, right? And vice versa, right? If we're subtracting, right, then subtracting it makes it bigger, right? 1/2, that becomes 1, which is in fact bigger than 1/2. Okay, so just keep in mind those two operations when dealing with the comparison test, right? And another thing that is helpful when dealing, because there's a lot of comparisons, so there's no like strict equality, which leaves a lot to it's not as clear, right? When we think of inequalities, right? So one thing to keep in mind is, well, all the series that we're dealing with, they deal with positive values. Okay, so we're always bounded on the lower end by 0, right? So positive value series, right? The lower end is always 0, right? It doesn't go below 0, right? So when we establish inequalities, we really are looking for some kind of upper bound, right? Or show that it's unbounded for divergence, right? Now, if you, in these limit comparison tests, when you have determined that as you compare it and you take a limit, right? Right, just keep in mind, or when you compare it and you know that you know the convergence and it converges to something, uh, if you show that some factor, some constant c, or just some term c, is less than infinity, this really doesn't tell me much, right? So just saying it's less than infinity, but as we see, there are different levels to infinity, so it doesn't really let me establish any kind of any kind of anything really about C. Now, if I were to show the opposite, right, that whatever quantity that I'm comparing actually is tending towards bigger than infinity, now this is useful, right? Now this is showing me that it's unbounded, right? It's a even bigger type of infinity, right? So this is helpful, right? So it's unbounded here. Whereas up top, right, it's not really clear. It might be, it might not, right? And same thing, vice versa. If you show that c is bigger than 3, well, that also is not helpful, right? If we want to determine whether something is bounded or unbounded, right? Because 5 is bigger than 3, but so is infinity, right? But what is helpful is if we establish that this c is less than 3, right? Because again, we established these are all positive value series. So if it's bounded by the lower end at 0 and up by 3, then I know that it's approaching some finite value in between. So that is helpful. Okay, so we'll just keep this in mind as we progress through our... So we're going to go over 2 comparison tests. One of them just called the comparison test, where I'll introduce it in a second. Another one is the limit comparison test, which involves taking a limit, which is more straightforward in the sense that you don't need to establish any kind of inequality of less than or greater than, right? You just really need to evaluate a limit and interpret the results. And there is some subtlety in that, and we will get to that eventually. But let's just start with the comparison test. All right. Okay, so here, let me, okay. So our comparison test. So it says, suppose there exists an integer n such that this holds, right? This inequality, right? Always bounded on the lower end by 0. A sub n is less than b sub n for all n. This second part here, n bigger than or equal to n, it means that it doesn't necessarily have to hold for all n. Excuse me, but after a certain time, after a certain value for n, then the inequality holds. And I'll explain with an example of that in a second. So first of all here, if we've established this inequality here of the terms of the sequence, right, of the series, if we establish that A sub n is less than or equal to B sub n, and I know, so again, I know that B sub n converges. In these tests, it'll be helpful to know a family of series that is convergent or divergent, right? For example, the P series, which we discussed previously, right? I know the convergence and divergence of those P series. Those are going to come in handy, right? Those are going to be helpful here to establish these inequalities, right? So if I can establish this inequality here for this part one, right, and I know B sub n converges, then A sub n will have to converge, right? Because it's less than some finite value, right? Now on the opposite end here, right, if A sub n is actually bigger than B sub n, which is bigger than 0, right? Again, always bounded by 0 on the lower end. Well then, if B sub n diverges, then A sub n must also diverge, right? Because it is bigger than B sub n. All right, let's kind of look at some examples here, right? So let's see. So we're going to be using the comparison test here. 5 over 2n squared plus 4n plus 3. All right, and I want to determine whether this is convergent or divergent. All right, now looking at this here, right, what always sticks out is I look at the leading term, right, in the denominator, which is an n squared, right? Again, don't really care about the 4n, don't even care about the 3, not even really the 5 over 2, but I will account for those in my comparison here. But that n squared, right? When we deal with large values of n, then that leading term is going to it's going to take over, right? So I want to compare it to 5 over 2n squared, right? Because I know the convergence of that. Right? Now here, since I'm adding these values, right, this whole term here will always be less than this, right? Since again, n is positive, all these values are positive, so this will always be true, right, for n bigger than or equal to 1. Okay? So that always is going to hold, right? So I know that here, 5 over n squared 2 is 5 halves the sum of 1 over n squared. This is convergent P series, and then multiplying it by 5 halves still is convergent, right? It's still a finite value. So this is a convergent sequence. And since the terms of the convergent series here, those are also getting smaller than a convergent one, then by the comparison test, therefore, right, by the comparison test, the sum of 5 over 2n squared plus 4n plus 3 also converges. Okay, and that is how we use the comparison test, right? Again, just having knowledge of the P series is going to go a long way here in determining convergence, right? Once you kind of get used to manipulating these inequalities, this test is actually pretty straightforward. All right, now let's take a look at another example here, right? Now the sum k is equal to 1 of infinity of ln of k over k. All right. Now, right away, again, right, when I always see this, I think of a P series. All right, now which one in particular, right? Looking at this, I think of this one, right? The harmonic series, which I know to be divergent. All right, so when I establish this inequality, what I would like to show is that this ln of k over k is in fact bigger than 1 over k. But is this true? Right? I mean, I could write it, right? Doesn't mean it's true. Now, what would make this true for this to be bigger than 1 over k? Well, it would be true if this quantity was bigger than 1, right? The ln of k, right? Then that would make this true, right? Because we can think of it like this. We can think of it as ln k times 1 over k, right? Bigger than 1 over k, right? The only way this works is if ln of k is bigger than 1. Well, when is that true, right? So we know here, that's our graph of ln of k, right? Here is 1. So at 1, ln is 0. So it's definitely not true there, right? 0 is not bigger than 1. So that inequality is not true there, right? And in fact, what do we know? We know ln of e is bigger than 1, right? And I know that the ln function is increasing, right? So after the number e, when it's 1, it will always be bigger than 1 because it is increasing, right? But when does that happen, right? E is the natural number here, where if this is 2, e is somewhere here. It's 2 something, right? Here, that's 1. So our next whole number, right, where it will give us 1 would be 3. So this inequality holds whenever k is bigger than or equal to 3. All right, so I just want to make sure that I've established that fact. Okay, so now what this tells me here is, since I know this is divergent, well, all of these terms are going to be bigger than the terms in a divergent sequence. So when I add them all up, they will be, in fact, bigger than the simple harmonic series. So therefore here, by the comparison test, the series ln of k over k is divergent, right? And again, it really doesn't matter that I started at 3, right? Those first 2 terms, those are finite, right? And that will not make it convergent. All right, it will not affect the convergence or divergence, any finite number of terms. Okay, so let's take a look here at maybe some about some that involve maybe the factorial. So let's take a look at the sum of 1 over n squared. Right, and I want to determine whether this one is convergent or divergent. Okay? All right, now keep in mind here that n factorial is equal to n minus 1, n minus 2, etc. all the way to 3 times 2 times 1. Right? Where here, 2 is really the, not really about 1, that really is not going to help me out here. So what I do is I'm going to establish this inequality, though the smallest number besides 1 is 2. So this product here, right, will always be bigger than, let's say if I replace all of these terms by 2, right? They'll always be bigger, except the 1, right? I'll just leave that one off, right? These terms here, right? What if I replace, because then that inequality wouldn't necessarily hold. All right, so then I just replace them by 2, right? This will, the inequality here on the left will always be bigger than this inequality, where here we have n minus 1 terms, right? Or that's 2 to the n minus 1. Okay, so now what I've established here is that n factorial is bigger than or equal to 2 to the n minus 1. All right. And now really I'm not after that, but actually the reciprocal. So when I take the reciprocal, I can just flip around the inequality. Okay. All right. And now that looks like my series, right? Now I've set up a comparison. All right. And then this term here, the sum, we can think of this as 1 over 2 to the n minus 1 from 1 to infinity. And this is geometric, right? Geometric series. Right, where the value here r is between 0 and 1. So what we have here is, this is a convergent geometric series. All right. We have a convergent geometric series. Excuse me. So that means that 1 over n factorial is less than these terms, smaller, of a convergent series. So therefore, by the comparison test, the sum of 1 over n factorial is also convergent by the comparison test. All right. Okay, so now let's take a look at one more example here. All right. Okay, so here, the example I want to take a look at here is here the sum. So another example here of n factorial over n to the n. Okay. All right. So here I want to, when I have something like this, sometimes what's helpful for me if I just list out what some of these terms look like, just to get an idea of what's happening to the overall term. So when n is 1, we just get 1 factorial over 1 to the 1. Right? So that's just 1. All right. When n is 2, right, we get 2 factorial over 2 squared. So here we have 1 times 2 over 2 times 2. Okay, and here what we notice here is, and then let's do it, after when n is equal to 2, this last term is always going to be 1, right? And the terms before that are going to be really less than 1, right? When n is 3, right, 3 factorial over 3 to the third, that's 1 times 2 times 3 over 3 times 3 times 3. Right? And if you notice here the pattern here leading up to the last term here, right, where it's 1, these other fractions, right, they're going to be less than 1. Right? Starting here, right? As you see here, the first one is 1, so that one, that pattern doesn't hold, right? If you see here, let's do one more. 4 factorial over 4 to the 4th, so that's 1 times 2 times 3 times 4 over 4 times 4 times 4 times 4. Right? That last one being 1, the largest term, and then before that is 3/4, 3/4, right? So what I can say here is that n factorial, right, is going to be less than, or over n to the n, will be less than or equal to these first two terms, right? So 1 over n times 2 over n, and then just setting the rest of them to 1. Right, for n bigger than or equal to 2. Okay, and the reason that works is because, well, the last term is definitely 1, and these other ones are going to be less than 1, so they'll be less than setting them equal to 1. Okay, so now what that tells me is, well, what it allows me to do now is, well, now I have n factorial over n to the n to be less than or equal to 2 over n squared. Right, and again, here, 2 over n squared. What we have here is a convergent p-series. Right, convergent p-series. So if the values of n factorial over n to the n are less than the values of a convergent series, then therefore by the comparison test, sum of n factorial n to the n is also a convergent series by the comparison test.